So far, somebody was giving us an image and we were outputting the corresponding text. Can we go the reverse route? If somebody gives us a text, can we start drawing images? Or can we ask our models to start drawing images? What do I mean? Somebody might give us this sentence. This small bird has a pink breast and crown and black primaries and secondaries. And based on that, the model should draw images of birds satisfying the properties that we described in the text. Or this other one, this white and yellow flower have thin white petals and round yellow stamen. And then it's gonna keep drawing different images for us. So that's a task description. Sometimes the flowers look good, sometimes they don't look that good, but now your model is doing some creative work. You describe something to it and it's starting to draw, starting to imagine flowers or birds. We are gonna see GANs later on. So you can think of this slide and the next one as teasers for what we are gonna be expecting in the rest of the course. But the idea of a GANs is not that hard. What are you doing? The model is gonna generate an image. We know that we have some images that are real. These are actual images from our data set. So some images are gonna be generated, some images are gonna be from the data. Now, what you want to do is you want your generated images to become as similar as possible to your data. So you're sort of learning to sample from a distribution whose formulation you don't know. You're learning to sample from a distribution in such a way that those images are going to become indistinguishable from real images. Now the question is, how are you going to write down a loss function for it? What is a good loss function? One option is to go the log likelihood route, which means that you need to know the formulation of your probability distribution, like what we have been doing for languages. But for images, it's a little bit hard. For language, every word in your sentence was coming out of a discrete distribution. You had a vocabulary size and you were sampling from that distribution. And no matter what you do, that was a discrete distribution. And you could use softmax to write down your probability distribution. Here you have images. Each pixel has red, green, blue in it, and each channel is a real value. Should you assume normal distribution here? But if you assume normal distribution, we know that our images have multimodal. The distribution of images is actually high dimensional and very complex. So a normal assumption is not a good one. And we're actually going to see that route. We are going to see that some people actually write down a probability distribution and then try to maximize the log of those likelihoods. Here is an alternative. What if you can actually learn your loss function? So now you're learning your objective function. And where is that coming from? We know that we are really good at discriminating between cats and dogs. We are really good at solving discriminative problems. What if you reformulate your problem as if you're discriminating between real and fake? It's a binary classification problem. And then that's going to give you a loss function. If you have a very good discriminator, and if you assume that you know your D, then this is going to give you a loss function. And what is that? Or your objective function. We shouldn't be calling it loss function. The generator is trying to make the discriminator make mistakes. And that's your entire loss function. That's your objective function. So the generator is going the reverse route of your discriminator, while the discriminator is trying to do the correct thing. It's trying to discriminate between real images and fake images. Images from the data, images generated by a generator. So that's the big picture. But whenever your loss function is coming out of a neural network, you can see that this G is already a deep neural network, is going inside another neural network. And then to be able to optimize over G, you need the gradients to pass through the discriminator for some signal, for some learning signal to reach G. So G is going through a nonlinear function, a deep nonlinear function. Usually optimizing this objective function is not going to converge. Equivalently, you are gonna optimize this other function, which is equivalent. You have 1 minus d, here is just d, and you get rid of the minus. And you change that minimization to a maximization problem. So this is what this generator is gonna do. Given d, it is trying to find g. The discriminator, given g, is trying to find d. And its job of the discriminator is to increase the probability of the real images and at the same time increase the probability of the fake images or of the generated images. So it's trying to do the correct thing. And 1 minus the probability of the generated images is actually the probability that image is generated. Why? Because d is the probability of that image being real. And 1 minus d is the probability of that image being fake. And there's going to be a competition between the generator and the discriminator. That's a quick overview of GANs. We are going to go into more detail later on and try to justify that objective function and why does it work, mathematically speaking. But what do we have for this problem at hand? You have a text, you have an image. We know that our text, we need to encode it somehow. We need to vectorize it. And let's say phi is given to us through some pre-training process. So let's say you have a text encoder. You can take G. Previously, this was unconditional. Now you need to condition on the text, on the description. You still have a Z here, which is a simple distribution, a normal distribution, or a uniform distribution. And while you take Z, push it through a nonlinear function, you're going to end up with samples that are no longer normally distributed. And the distribution is going to end up being super complicated. You will start with simple distributions, push them through a nonlinear function, and then that's going to give you samples from complex distributions. So it's the same thing. You have Z here from normal distribution or uniform distribution. You have phi, which is the vectorized version of your text. Your discriminator is also going to be conditioned on the vectorized version of your text. And this is called conditional GANs. And then you're going to write down your algorithm. It's a little bit more complex than what you see here. What do you have? The algorithm is called GAN CLS. Not only is trying to do these objective functions, it is trying to be discriminative as well, your discriminator, when it comes to classifying images and text. Let's see what happens. You have a text, you vectorize it. You have a text, you vectorize it, but this is a caption for a totally different image. Maybe you have this caption, this white and yellow flower, which is a caption about flowers, and you try to associate it with this image, which shouldn't happen. This is the wrong caption for the wrong image. And this is the fact that we know, wrong caption for the wrong image. So you have two representations for two different texts. You draw a sample from normal distribution. You take that sample vector, you take H, which is the vectorized representation of your correct text, and then that's going to give you your generated image. Now you're going to have your discriminator outputting 3 numbers, 3 scores. If you have the real image and the corresponding correct text, it's going to give you SR. This probability you want to maximize, so that's going to go inside this log of probability. You have the correct image and the wrong text. It's going to give you SW. That probability you need to minimize, which is equivalent to maximizing the log of 1 minus that score or that probability, because this is the wrong association. You want to penalize that. In a similar fashion, you want to penalize fake images being associated to the correct text. This one has to go down as well. S has to go down. Equivalently, you can maximize log of 1 minus S. That's going to give you the loss of your discriminator, and you see it is different from what you have here. It's different from what you have there. It has this additional term, real image, wrong text. But this log of SR plus log of 1 minus SF is going to give you this objective. And then given that you know your G, you're going to optimize over D. You take 1 step of gradient descent in the direction of minimizing that loss. The generator is going to look at the generated images. The corresponding is F. You have a fake image, you have the correct text for it, and then you are trying to maximize this guy. Log of the discriminator operating on a fake image. And then you're going to update your generator. One step of that, one step of this, and then, or a couple of steps of your discriminator, one step of your generator. And then after a while, your generator is going to generate images. In the next session, I'm going to tell you what is this fee, how do you actually pre-train it? Are you going to pre-train it only on text? Are you going to pre-train it only on these captions? Or are you trying to encode some notion of images inside this fee? And we are going to go the second route, try to encode some notion of images in fee. And we are going to do some modification to GAN CLS as well. And then that's going to be able to generate images that are reasonable or reasonable looking. I think I'm going to stop here. For those of you who have questions, I'll be around.